Hello everyone, I am Anmol Kapoor and I have been allotted lecture number 11 as video assignment. Lecture 11 covers basics of Poisson random variable. We are going to discuss a brief theory about the topic and do a question related to it. So Poisson random variable is basically an approximation for calculating probability by taking probability mass function to be equal to e power minus lambda into lambda power I upon I factorial. Here lambda has to be a finite quantity. Also note that the expected value or the variance of a probability distribution will be equal to the parameter lambda. If we take lambda to be equal to n into p, then if n is tending towards infinity, p should tend towards 0 for having lambda to be a finite value and to have Poisson implementation. Now we are going to discuss this question, which is based on the previous theory. We are having 1 nanogram of plutonium-239, which is a radioactive material, and it has 6.89 radioactive decays in 3 seconds. And it is given to us that it follows Poisson distribution. So first we are going to justify that why it should follow Poisson distribution. We know that 1 gram has approximately 10 to the power 23 order of atoms. So 1 nanogram will have order of 10 to the power 14 atoms, which is very, very large. So n comes out to be very, very large. So we have our n to be very large and consequently p becomes very small. And therefore lambda comes out to be finite and we can apply Poisson in this case. Also, later on, we'll find that the expected value or lambda is also a finite value, which makes us more clear to apply Poisson's equation. We are asked to calculate probability that in 1 second period there is exactly x radioactive decays, and we have to plot it with respect to x. So seeing this formula, if we put small x in place of small I, we'll get e to the power minus lambda into lambda power x upon x factorial. Here, lambda has to be found out. From this slide, it is written that expected value or the variance of probability distribution would be equal to lambda. Here, we were given that 6.9 radioactive decays happens in 3 seconds. So in 1 second, we have 2.3 decays. So lambda comes out to be 2.3. Also, the other part, to plot the random variable equation with respect to x, we are going to do that. This was basically the main function that we got, the final function of probability in 1 second period of having x radioactive decays. Putting values of x is equal to 0, 1, 2, 3, 4, 5 and so on, we got this as a graph. We see that as x tends towards infinity, probability tends towards 0 and we have a maximum at around 2. Also, continuing to the question, we have that we are required to find the probability to have radioactive decay greater than or equal to 6. We know that probability of x is equal to 1 minus probability of x complement. Therefore, required probability is equal to 1 minus probability of having decay less than 6. So 1 minus 1 p0 plus p1 plus p2 plus p3 up to p5. Putting the values from the graph itself, we got our required probability to be equal to 1 minus 0.965, which is equal to 0.035, which is very much low. So here, if we see that at values greater than 6, we are having the graph tending towards 0. And also calculation of probability justifies that the value is indeed very close to 0. So our result is fully justified. Also, we are asked that what would happen if we would have doubled the period of observation. Here, period of observation was 1 second in the previous case, but now we are doubling it, so period of observation becomes 2 seconds. So lambda changes because lambda is the expected value and we had lambda equal to 2.3 for 1 second. So for 2 seconds, we would have lambda equal to 4.6 decays. So lambda is now 4.6. Now putting in the formula of Poisson random variable equation, we got our probability of having decays equal to x at 2 seconds to be equal to e power minus 4.6 into 4.6 power x upon x factorial, which is equal to e power minus 2.3 into 2 to the power x into p for 1 second. So the ratio is dependent on 2 power x and it increases if we increase the value of x. Thank you.